Okay, everybody, welcome to the second day of this week's program. We are starting with Mordehai Milgrom, who's going to tell us about the MOND-cosmology connection.
Thank you, Nilesh, and thank you all. So as you all know, I'm sure dark matter is being invoked in galactic systems and in the universe at large, because the baryons that we observe really fall very short of providing enough gravity to explain the dynamics, the motions in galaxies and the expansion of the universe, the formation of structure and so forth. So the natural explanation for this would indeed be to add some matter, the call dark matter, that provides the extra gravity if you just place it correctly in the correct places, with the correct distribution and so on. But you can also take another approach and say, no, there's not much matter that we have not observed to speak of, and baryons are all there is. And they provide the gravity that's needed, because the gravity that we use, Newtonian gravity and general relativity, when it's needed, is simply has to be modified in the under the conditions that prevail in those systems, the universe and galaxies. So MOND is indeed such an approach. It was proposed some 40 years ago, and it takes the following view that if you want to modify gravity but still retain all the successes of standard dynamics, say in the solar system, in the lab, and so on, you need to identify some system parameter, system attribute that is very different in galaxies than in the solar system. So you can hinge the modification on this parameter. And to make a long story short, what I in the end settled on was the acceleration. So it turns out the acceleration in galactic systems is many typical accelerations are many orders of magnitude smaller than what you find in the solar system. For example, the sun goes around the galaxy with a velocity that is 10 to the 8 times smaller than that of the Earth around the sun. So, as is always the case when you want to modify it in such way, you have to introduce some new constant that will tell you where the boundary between more or less the applicability of standard dynamics and the new regime is. So in this case, it has to have dimensions of acceleration. And it will also, of course, enter very ubiquitously in phenomena in the modified regime. So there is a lot that has been said and done about this for over the 40 years that's been around. But today I want to concentrate on a rather narrow aspect, but potentially very important, having to do with some indications that this constant, or at least its numerical value as we deduce it from many independent observations, is very near in value to accelerations that are typical of cosmology. So this is an introductory overview. I'll give a very brief introduction to MOND, just explain what it is. Then I'll show how this constant appears in many ways in data, in a lot of data. I'll point out the coincidence, which is the basic fact that I'm going to discuss some practical implications, namely, even if this coincidence is a coincidence, no more than a coincidence, then it still has some implications for phenomena in astronomy. And then I'll very briefly touch on some qualitative ways, perhaps, to understand how this connection comes about. So, okay, so these are essentially the defining axioms for MOND. As I said, it is a theory of dynamics that modifies. So you allow yourself everything, not just modifying gravity. I also by modified inertia, I mean that you don't only modify the Poisson action or the Einstein-Hilbert action in the case of relativity, but also perhaps matter actions. Anyway, it has to be viewed in a more general scope. And you introduce a new constant, A naught, to restore standard dynamics for high accelerations, right? we basically can say that formally that all results, all MOND results, or all MOND equations of motion or MOND Lagrangian should go to the standard ones. In the limit, the formal limit where A0 is taken to 0. Just that you get classical dynamics from quantum by taking H bar to 0. And the novelty is, of course, in the opposite limit, when all accelerations in the system, or at least some of them, are smaller or much smaller than this A naught. So formally, you can achieve this again by taking A naught to infinity. Well, it turns out that, again, the formal procedure would be to take A naught to infinity, but also G to 0, so that so this constant A naught, which is G time A0, is kept fixed. And in fact, I tend to think that this constant is more really basic than A naught, and we should think of this big A naught, and that A naught is just big A naught over G. At any rate, as is always the case, also we have to assume, in order to be able to derive some important results from this, that the theory does not contain, say, other constants with dimensions of acceleration that are very different from A naught, or dimensionless constants that are very small or large compared to 1. But this is always the case, like in relativity or quantum mechanics. So yeah, I also like to draw this analogy in the sense that A naught plays, as I said already, both the role of the sort of dividing line between applicability of standard dynamics, but it also appears, as does H bar, for example, in quantum phenomena, it appears in practically all phenomena of the dynamics in the low acceleration regime. So this can be taken as an effective definition of MOND, and I'm stressing that it is not modifying gravity at large distances, about which we have much yesterday, I mean. And in fact, you can show that the modification of the distance dependence of gravity cannot work. It's absolutely, it cannot work. I mean, if you want, I can explain why very briefly. Okay, so yes, I'm sorry, but I didn't say, this is the essence of the modification. You want it in the deep MOND limit. It's not how the idea was formulated in the beginning, but then we came to realize that this is a neater way of describing it. At any rate, it's a good mnemonic. So you want your dynamics to become space-time scale invariant, even in the non-relativistic regime. So here I'm just trying to explain what this basically means. It means that, say, if you take any self-gravitating system, sorry, I'm pressing the wrong button again. Let's say with its whole time history, okay, and which is a solution of your equations of motion. Yet take another history gotten from this by just inflating all distances and all times by the same factor. So it's another legitimate history. Okay, so Newtonian dynamics isn't scale invariant, of course. It's the equation A scales like 1 over lambda if you scale everything by lambda, and the forces are scale like 1 over lambda squared. In order to make this, to get something that is scale invariant, so this is a caricature of what the deep MOND limit is. So it replaces MA equals F by basically MA squared over A naught equals F. And this makes this left-hand side also going like 1 over lambda squared under scaling. So this would look like modifying inertia, but you can invert it basically and get an equivalent thing, which is modifying gravity. Good. So yeah, so these are the basic axioms, and as we shall see, just from the basic axioms follow a large number of very strong predictions. Might be surprising, but it's the case. It happens. It has happened in quantum mechanics, for example, just before Schrödinger and Heisenberg. We had many important results that follow from the quantum concept: black body radiation, photoelectric effect, specific heat of solids, Bohr atom, of course, and so it is here. But of course, you want a theory, you want a complete theory. They're just the basic axioms do not predict, all situations and so on. So you're looking for theories that embody those basic axioms, and then you are assured that they will automatically satisfy all those important predictions. Okay, so just again, very briefly, there's one theory that replaces the Poisson equation by something that looks like the equation for a dielectric medium with a field-dependent dielectric constant. And this mu function is introduced by hand, essentially. And it has to have two limits. So in one limit, when A0 goes to 0, the argument goes to infinity, goes to 1 to get the Poisson again. And the opposite limit has to become linear in its argument so that you get scale invariant. This is another theory, relativistic theory. These are the field equations, but I should say that they are derivable from actions. And so I have all the standard conservation laws and so on. Right. There are also quite a few relativistic theories that have been proposed. So a relativistic MOND theory, by definition, would be one that in the non-relativistic limit goes to a non-relativistic theory that satisfies the axioms, because the axioms were formulated for the non-relativistic case. So again, without, so the first, I mean, there have been some precursors to this, but the first really full-fledged and good theory that gives correct lensing, for example. I mean, for lensing, so of course you need a relativistic theory for example, for lensing, but also for cosmology. So the first really one that gave correct lensing, and so was Bekenstein's Teves theory. We had some adaptations of Einstein ether theories, contributions, camouflage adaptations also. Right. I don't think this actually exhausts all of them. Some non-local extension of GR, my own theory, a bimetric theory. F of Q, we heard about F of Q yesterday, so there are also adaptations of F of Q theories that have a non-relativistic MOND theory. Okay, so some of the immediate consequences. For instance, take a body of mass n and consider some test particle orbiting it, and now just apply this scaling. So under scaling, the radius of the orbit changes. Velocities do not change because they are lengths over time, so do not change by scaling. And masses also do not scale. So immediately you see that this theory, the scaling invariants predict that the orbital velocity of a test particle around some massive body will be independent of radius. Okay, unlike V going like 1 over square root of R in Kepler, Newtonian dynamics here, it becomes constant, and this of course underlies the prediction of asymptotically flat rotation curves we speak about before. It also, okay, so you have this velocity. What can it depend on? Now it can depend only on the mass. It's the only parameter. And you have the mass and A naught and G at your disposal. And the only expression with dimensions of velocity that you can construct is the force root of M. Yeah, I should say that in the deep MOND limit, it's only this big A naught that can appear. A naught and G, small A naught and G cannot appear separately. Essentially, you can argue from dimensional arguments that only constants can appear that have dimensions that do not change if you scale the units of time and length by the same factor. But A naught and G separately do change, but this big A naught does not change. But you see from here that it has dimensions of velocity to the force over. Okay, so you would see that in deep MOND, in the deep MOND regime, namely in phenomena that involve only very low acceleration compared with A naught, only this big A naught can appear. So this is a very strong prediction. Yeah, okay, so I'm trying here to if you try to interpret those observations in terms of dark matter, then are they telling us something about only halo property or baryons and halo? So of course, asymptotically, the velocity is completely dominated by the halo, so the fact to say that the velocity, or if you want to reconstruct it with dark matter, you have to say the halo has to have a density going like 1/r to reproduce. But anyway, it's a property of the halo. And this relates the property of the halo, which is the infinity squared, to the mass of the baryons. Remember, all masses here are baryons, there's no dark matter. Okay, so it's like a halo baryonic connection. It's a very, I think, telling point because, well, I'm not sure I'll have time to discuss in the detail, but we know that in galaxies, the baryons constitute only a small fraction of the dark matter, a fraction that is much smaller than the cosmic value. So if the cosmic value is about 1 to 6, in galaxies you find even 1 to 1 in 100 ratio. So the dark matter explanation of this is so-called feedback, saying that most of the baryons have been somehow kicked out of a galaxy in the course of its development and so on. But so very little is left. But MOND is telling you that this very little, sort of this tail works the dark matter halo dog. Okay, so this is a point. I'm not here to advocate MOND, I should say, so I'm not giving arguments for MOND or against dark matter. But anyway, there are such arguments. Okay, so now this applies to any galaxy, even if it is in the high acceleration regime within its bulk. Then going far outside of the galaxy, of course, you get to the low acceleration regime. So for all galaxies, you expect this. But there are also galaxies that are all in the deep MOND regime, namely everywhere in the galaxy, the accelerations are very small. And so there is a virial relation or an analog of the virial relation for this such galaxy relating the total baryonic mass again to the velocity dispersion. Again, you can just derive this. Okay, you can show that there is some coefficient here of order unity. Okay, it can vary from system to system, can depend somewhat on system properties, but has to be of order unity. Another thing is that, okay, you look at the galaxy, and as you know, in some of these galaxies, at the center, the accelerations are high, and in fact, there's no need for dark matter. So originally, what the statement was that, yeah, when you look at the galaxy, initially it behaves like in Newtonian physics, but as you go to larger and larger distance, sort of the need for dark matter sets in at some point. But what this says is that it always sets in not at, say, a given radius or universal radius, but it sets in at the universal acceleration, which is A0. So in different galaxies, it occurs at different radii. Okay, never mind that. I may come back to that when I show the data, so I should just skip it here. In a way, you can actually show that, okay, so this some property of baryons alone, essentially. So, okay, there's also an issue with stability. You may know that dark matter is invoked not only to explain dynamics, but also to provide extra, or at least it provides extra stability to these galaxies. So thin self-gravitating disks tend to be unstable to bar formation, and then they just destroy themselves. So originally, in fact, Peebles, Ostraker, and so on, Yechiel suggested dark matter halos to stabilize disks. Now, MOND does have also a stabilizing effect. So it's important, and it enters some predictions, but I leave it for now. Yes, so the final point was that, in fact, from all this, you can see that you practically predict the full rotation curves just from the basic tenets. And if not, then you use a theory. And indeed, rotation curves are basically the flagship of testing MOND, because they are the most, first of all, the most reliable data that exists for them, but also they are there are many of them, and they are of different types, and you can probe different corners. So I show two, and rotation curves have been analyzed in MOND for the last 40 years in many studies. And so I just show two such panels. Each is superior in another way. That's why I'm showing both. So this they call the spark sample. Actually, it's only part of it. It didn't fit into one transparency. So what you see are rotation curves. The points are the data. The thin lines here, I hope you can see, are what you get from Newtonian dynamics. Namely, if you take the mass distribution, observed mass distribution of the baryons, you calculate the Newtonian field, and then the rotation curve that should result, and you get those little things. And the lines that essentially go through the data are the MOND. I should say the fits, because in this case, well, okay, there is, for example, the mass distribution of the baryons that determine the Newtonian acceleration field is gotten by looking at, say, the distribution of stars, of stellar light. And you need to convert stellar light to mass. And that involves a parameter called the mass-to-light ratio, as you may know, that is not known a priori for a specific galaxy, but there are theoretical estimates, and there's a lot that can be said. So, but here, let's say it is left as a free parameter, but it shouldn't be very different from what we expect. But you see that with one free parameter, you essentially get very well agreement. And this panel is a smaller one. What is good about it that here the galaxies are dominated by gas, and the gas, we don't need a conversion factor. We can measure the actual density distribution directly. So because they are dominated by gas, there's no need for this extra fit parameter. And so what you see are, again, the measured rotation curve, the one that you would get from Newtonian physics. And these lines are now a parameterless prediction, just prediction, no parameters, no nothing. So I think they're quite impressive, and even in reproducing some of the wiggles. Now you see some differences, but okay. Why? Because, for example, the distance to these galaxies that have been used may not be quite exactly what it is. And so, but to avoid claims of fitting, so just distances, inclinations, gas distribution were just taken from the literature. Okay, so now some.
Sorry, a question. So, yes. How do you choose your value of A naught here?
Okay, so there's of course one value of A naught that is good for hundreds of galaxies.
So you fitted it to all the galaxies and then got.
Well, initially what people did is it's a sample that I didn't even show from the late 80s. Yes, they fitted each galaxy separately with an A naught, and then you take one A naught. But my favorite way of doing it is, in fact, from here, because okay, so there is this second prediction, this one that says that the asymptotic speed should, or the mass should be proportional to the asymptotic speed. So, so this is a plot of this relation. What's plotted here is indeed this is the V final. So the asymptotic speed for each galaxy, each point is a galaxy, and MB is the total baryonic mass, which includes stars and gas. And so the prediction is only that there would be a line with a slope of 4 here, which it is. And so again, my favorite definition or normalization of A naught is such that there's actually equality. Okay, so for this value, so the A naught fixed once and for all from this quantity is set and can be used in all galaxies. Yes, and you can see that it can increase. But again, the emphasis here is that you can, well, in this case, define A naught from here. And in fact, each galaxy basically defines, you need A naught. I mean, it defines it. With a different A naught, it would not agree. So clearly, this is essentially a summary of many rotation curves. So it is in the following form. What is plotted here is, okay, it says v square over v bar square. So the measured velocity square over the velocity you would determine from the baryons from Newtonian dynamics. So you could call it the discrepancy. Okay, it measures how much dark matter units are within this radius compared with the baryons that you see, and it's plotted against the Newtonian acceleration. Newtonian acceleration is just mg over r square for a spherical system, but actually it's done correctly, of course. For these galaxies, it is calculated from the disk distribution and so on. And okay, so this is basically another rendition of the same plot with more data, and it's more modern. So I'm also showing it, but this is really what I want to discuss. So, okay, so at high acceleration, you just expect this value to go to 1, so Newtonian. So this, as I said, is the departure from Newtonian. The total amount of dynamical, let's say, mass that's needed, or the measured acceleration divided by the Newtonian acceleration goes to 1, and MOND predicts this behavior okay, with, and I should say A0 enters here in 3 different and independent ways. So one is just where the crossing between the 2 asymptotes is the transition. And in this region, it enters in 2 ways, because the contribution to this branch comes from two different types from the Redshift galaxies. So one are just asymptotic velocities in galaxies, so on the asymptotic branch, and the other is from galaxies that are completely in the deep MOND regime. Anyway, you should believe me. So really A0 enters in 3 different ways here. This is again the same thing. It's plotted. What is plotted is just G observed over G baryonic or G Newtonian. So at high acceleration, it should go to 1 to 1, and here it is predicted to be this. There is in fact an extension of this to much lower accelerations from weak lensing, which I'm showing here. So this is what you saw the previous slide. So in galaxies, you can only go as low in acceleration as this, which is about typically a tenth of A0, maybe somewhat less. So A0 is here. So it's about a tenth. With weak lensing, you can go much further. You go to actually to maybe half a megaparsec or even more. But what this is telling you is essentially that rotation curves of galaxies on average, because as you know, weak lensing is a statistical analysis over many, summation over many galaxies. But then anyway, statistically, rotation curve remained flat to very large radii. So,
sorry, what is G bar?
G bar is the baryonic. Yeah. This comes from different analyses, so they use. I mean, I'm just copying the transparency. And you could ask about this, but anyway, it really goes very far. See, so 4 orders of magnitude low A0. Right. Not much. Okay, so maybe I should just skip this briefly, but it's another prediction relating to. I should say, maybe I should have said it before, that those predictions I mentioned are independent in some sense, that in the sense that, say, if you try to explain them in terms of dark matter, then they are not derivable from each other. Namely, I could build galaxy models with baryons plus dark matter that will satisfy some of these relations, but not the others. Okay, so they do not follow from, say, if I take 2 of them and say, okay, it's enough in dark matter to explain 2 of them, and all the rest will follow. This is not the case. So that's another one. It is relating to, pertaining to a relation between the central surface density of a disk galaxy. So now you don't even have to know the full mass distribution in a disk galaxy. It's enough. The parameter that appears here is just the baryonic sigma 0, which is a central surface density of just the center, at the center, and it can be related to the central surface density of the putative dark halo, if you want. Okay, and again, so actually, I think the next slide, right, it is also a similar phenomenon. An acceleration is essentially equivalent to a surface density. A surface density is mass over area, namely mass over r squared. So if you multiply by g, you get an acceleration. So A naught over g has dimensions of surface density, and it's not surprising that it plays a critical role when you discuss surface densities of galaxies. So it turns out that the correct quantity to look at is A naught over 2 pi g. This 2 pi comes from the 4 pi of the Poisson equation. It doesn't matter, but it's not A naught over g. So what people did here, they fitted rotation curves with, in fact, unrelated to MOND. They fitted rotation curves with the baryon plus dark matter halo, and they calculated the column density of the halo at the center, integral of rho dl along the line crossing the center. And they plotted this quantity. Actually, they fitted the halo with some chord isothermal sphere or something like this. But anyway, this is a quantity equivalent to this. And they, lo and behold, they found some universal value. Yeah, I'm glossing over some details here necessarily, but the predicted value for this is this. So shown by the arrow. So again, very good agreement. But the point here is that you can deduce A naught also from this. That's another thing. Let's skip it because there's not so much time. But anyway, this concerns galaxy groups, so not galaxy now. You look at all groups of galaxies and you measure the total baryonic mass and the velocity dispersion. It's a rather less well-defined analysis because you're not sure about the projection effects, and but anyway, so you see a large scatter, but anyway, this line going through the data is what MOND would predict for this one. Right, so this in summary, so we have a situation.
Sorry, can you go back? I don't think I understand what this plot is. So what is the x-axis here?
Okay, it's A naught over the So G is actual measured acceleration. Let's say right. Sigma square. Let's say you measure velocity dispersion, okay, in the cluster, and you know its size. So sigma square over right. R times the appropriate geometrical factor gives you the acceleration, the actual dynamical acceleration. It's an analog of V square over R.
So to the right is the MOND regime here, because G is small to the right.
Right.
Okay, I see. Good. Thank you.
Sure. Okay, so it's just a philosophical, historical point that I want to make. We have a situation, even without even discussing theories or the validity or the self-consistency, or we have a situation where phenomenologically we have, you see, irrespective of MOND, this A naught is a constant that appears in the data, and it appears in many different places and with the same value. So there have been a historical situation like this. This is taken from Perrin's book concerning the Avogadro number. Again, historically there have been many ways to determine the Avogadro number. They all get the same result, and he's wondering, I mean, it must be telling us something. And in those cases, it was the molecular or atomic nature of things. But there was a similar situation in quantum mechanics, where in the early 20s, I read Planck's Nobel lecture, and this was again before Schrödinger, before Heisenberg, before there was a theory, but he was pointing out very cogently that there are many phenomena in which this H appears. And he says something like this: it must be telling us something, there must be a theory the theory will eventually come, and so on and so forth. So maybe we can learn something from this. Anyway, so MOND and cosmology. So there is, of course, the big question of whether we can write a relativistic theory that goes to a non-relativistic MOND theory and give us cosmology correctly. So we know dark matter is invoked in cosmology to explain expansion in expansion history, structure formation, the CMB, and so forth. So is it possible at all? So for many years, we did not, some of those relativistic theories that I mentioned before have been checked for this, of course. And they were not satisfactory in this regard. But just very recently, there is this theory. It's not the topic of my talk. I just want to talk about the A0 connection with cosmology. But anyway, at least it is gratifying to know that there is one theory that claims to give MOND in the non-relativistic regime and to reproduce CMB and even structure formation and so on. May have its issues, but I ought to say I don't think we have yet a good relativistic theory. Just the other day I was talking to Luc Blanchet, who isn't here anymore, but he told me that he is also working on a theory based on MOND adaptation of there's a Kronon with Ojava gravity that also reproduces CMB correctly and so on. But that's not the topic. The connection I'm speaking of just simply has to do with the neo fact that this A0 is so this is the essence of the connection. If you look, turns out it's better to look at this quantity, and then if you look at it, it's very near in value, I should say, to some acceleration that you can define in cosmology. So one is just C times H0, C divided by the lifetime of the universe, or by expansion rate. And another one is this. So basically, just C square of the theta radius, let's say. And the fact that they are very similar is, of course, the coincidence that today cosmological constant is just a fraction of the closure density. And I mean, it's not a very dominant and it's not very subdominant. So, but it's the same coincidence. So regarding A0, these two connections can be made. And of course, which one it is, if any of them. So okay, so that's just the connection. You can also define, say, a MOND length, which would be C square over A, and in some physical context, it is more maybe appropriate to speak about length, comparison of lengths, not of acceleration. But okay, so you could say that this MOND length defined in this way is of the order of the size of the universe as defined by the theta radius or by the Hubble radius. Right, so a question immediately arises whether we should take this seriously at all. So in the sense that, for example, should we require that our theories reproduce this relation, or we just ignore it and, embrace theories that don't particularly have this, or in which A0 and lambda for, I should say that my own reference is this identification. Depending on which one you make, of course, for example, if you make this one, and since H0 varies with cosmic time, it's just today that it has this value, then you could say that maybe A0 varies with cosmic time, like there was in Dirac's large number hypothesis. You could actually tell in principle whether A0 varies by looking at high redshift galaxies and fitting their rotation curves and see what A0 they require. And there's just preliminary analysis at redshift of 2, and shows that it is at least consistent with A0 at z equal to being the same as it is today. So, right. So by taking it seriously, it's what I explained. So of course we know that there are coincidences that are meaningless. We don't have to pay attention to any numerical coincidence, but there are, it's just, I'd like to mention here that historically, the Weber and Kohlrausch measured this quantity by just doing experiments that have nothing to do with speed of light. They just measure Lorentz forces with charges, discharging Leiden bottles and so on. And they found this property of the vacuum, and a number that was very nearly equal the speed of light as it was known, but they did not make the connection. They missed the opportunity to say that light is an electromagnetic phenomenon, and that came only with. So maybe we should be careful not to ignore such. And you can then ask, okay, so why acceleration? I'm being asked quite often. I mean, all of a sudden, we are used to modification at large distances, at short distances. At the distance sounds more palatable, maybe. Why acceleration? What's so special in acceleration? So, of course, we immediately realize that acceleration defines a length scale that comes with it, which is c square over a. And for example, it's if you have an accelerated observer, the Rindler radius is of that order. It's the typical radius of the wavelengths of the Unruh radiation for an accelerated observer. And so on. So saying that A is much larger than A naught is saying that this radius that comes with it is much smaller than the cosmological radius. And then perhaps you could say that an observer with acceleration much larger than A naught doesn't sense, in this regard, doesn't sense that the universe is not non-trivial. For example, it is the theta and so on. Whereas when A naught is much smaller than, where A is much smaller than A naught, then this radius that you are, say, probing maybe, is much larger than the theta radius. Okay, so that is a point I already made. Right, so there are several, not practical, of course, they are not practical in the sense, but in astronomy, they tell us something interesting. For example, it turns out that you cannot have a highly relativistic system that is also in the MOND regime. So if you require low acceleration, namely mg over r square, let's say a black hole, so if you require the acceleration at the Schwarzschild or several Schwarzschild radii to be much smaller than A naught, it implies that the radius of the black hole is larger than the size of the universe, just because A naught is c square over. So, yeah, to me, all of this. So one approach in going about cosmology would be, okay, we have a MOND theory. Let's write a relativistic theory that reduces to those non-relativistic MOND in the Newtonian regime. And this is what has been done with all those theories that I described before. And let's see what it is telling us about cosmology. Okay, so in my opinion, all this is telling us that perhaps we should try to understand cosmology and MOND as a part and parcel of the same theory, not first derive some relativistic theory just to explain MOND in galaxies, galactic system, and then see what it's telling us about cosmology. This sort of seems to me that the whole structure has to be solved at, in one go. But anyway, this might be a hint of it because it's telling you, look, anyway, what's the point in deriving a relativistic theory when in any case, you're not going to be in the MOND regime for any relativistic system like a black hole. Only in cosmology, you get into a big MOND regime. Right, and the other, for example, another implication, for example, is that you don't have 5 minutes? Okay. You cannot have strong lensing in the deep MOND regime. So strong lensing like the Einstein ring and so on for object at cosmological distance, I'm saying. And that again comes from the fact that, so you have strong lensing in the vicinity or within the Einstein radius of an object, and then you can, okay, you can define a MOND radius for a given mass, which tells you beyond which radius you get into the MOND regime. So below the MOND radius, accelerations are high, you're Newtonian, and so this defines the MOND radius, mg over a naught. So the ratio of the Einstein radius to the MOND radius is, for cosmological lenses, is the distance to the lens divided by the MOND radius, which we know is cosmological. So you see that as long as the distance to the lens is not rather large than the Hubble radius, the Einstein radius is always within the MOND radius. So strong lensing occurs in the strong MOND regime. Right, so I think what comes next are attempts to, right. So now, what can we make of this coincidence? What sort of ideas, at least, I should say that I don't think that we have really a fully satisfactory explanation of it, but, and so that I will have to leave you with this puzzle. Perhaps something good will come out of it if you think about it. But it actually does occur in some theory in the following sense. So some or almost all the theories, the relativistic theories that I just listed before, have this form that the Einstein-Hilbert Lagrangian is replaced or is corrected by something that looks like this. It's some function of something, and this is a dimensionless function, so it has to have some length scale here. And this Q is, okay, in Teves, for example, it's the gradient of the scalar that enters the Teves. In f of q theories, it is the q, it is the scalar constructed from q by metrics. Anyway, it involves first derivatives of the metric, usually in those theories. So what happens in the non-relativistic regime, this q goes to grad phi over c to the fourth, where phi becomes the MOND potential. This f is this mu, or at least it is gives rise to the function, what we call the interpolating function of MOND between the Newtonian and the non-Newtonian regime. And so you see that inside here you have L square over c to the fourth, which is just 1 over a square, a0 square. So the argument of f becomes grad phi square over a0 square, which is just what you need for MOND dynamics in relativistic regime. And this, okay. And outside, okay, this L also appears. There's no reason that the same L should appear here and here, but if it does, then you see that, for example, when a constant contribution to F is just a cosmological constant with this as a de Sitter radius. And so if the same L appears here and here, it automatically gives that A naught is of the order of the cosmological constant. So I would say it's just an issue of economy, but it's not really a physical explanation. Because in principle, you could have different values. But if you accept this idea of economy, let's not, if we have to use a length scales in two worlds, here and here, let's use the same constant, then automatically you get this connection between lambda and A naught. But other ideas that are trying to be more physical, so this, as I said, happens in all those theories, by metric MOND, in F of Q. Right. Let's skip this. It's just okay. So the other ideas that are more physical indeed take advantage of the fact that with an acceleration comes a length or wavelength, and that MOND enters when these wavelengths become much larger than the size of the universe. So it's just an analogy here for that something like this happening actually in known microphysics. So these are gravity waves in a pool. The pool is of depth h, and it's under Earth's gravity g. So if you write the dispersion relation for the waves, you see that the dispersion relation knows. So you only measure the surface, okay? You measure things at the surface, but you know about the depth, because there is a transition, of course, when the wavelengths goes from being smaller or larger than the depth of the pool, and in fact the transition is very similar. This analogy with MOND with very similar limit if you make identifications of properties here, properties of MOND. Right, last point and last transparencies. I don't have the conclusions. They are self-evident, I think. Okay, so many years ago, I had this idea that, okay, Anu radiation is telling you that the observer moving at a constant acceleration, internal acceleration, sees itself embedded in a black body with temperature T. So maybe the F equals ma of Newton is really telling us that somehow there is a restoring force of the vacuum on accelerated observer that is proportional to the temperature. It's just by sort of Le Chatelier principle tries to bring the temperature down to zero. So it's a reaction inducing an action reducing some reaction. It's try to cancel the effect of the acceleration. But if you are in a de Sitter, then the temperature that you see is not the acceleration, but it knows also about you also record an accelerated observer in de Sitter actually sees an analog of. It's a combination of Anu and Gibbons-Hawking radiation with a temperature that is given like this, so A squared. It's acceleration in the Sitter and plus A lambda. Okay, and if now you say that the force is proportional to, okay, so T lambda is the minimum that you can have by just bringing the acceleration to a stop or stopping the acceleration. And if you assume that F goes like, so the restoring or the resistant force to acceleration goes like T minus T, you get an expression that actually gives MOND, namely it gives a behavior, okay, it gives an inertia that is not MA, but MA times U of some A over A lambda, and A lambda, then A0 appears to be A lambda, and it even has the correct behavior at low and high accelerations. So that is my final slide. I leave you with that. Thank you.
Thank you. Questions for Mati?
It's a question about what you said about there is no deep MOND regime for relativistic objects like black holes. So if I have a neutron star or a compact object in the center, the acceleration will be zero just by symmetry, right? So it will be probably a small region, but yes, their MOND should be active, yes, right? So do you
very small,
very small region? Do you think there could be any
utterly
effect?
Small, yeah.
It's similar to the idea of the saddle point in the solar system.
The acceleration on Earth is 10 to the 11 times larger than A naught. Okay, so for a neutron star.
No, I was thinking maybe, I mean, astroseismology. I mean, can it affect the propagation of waves?
So I should say, of course, there is a lot that can be said about experimental tests of MOND in the lab, on the solar system. But yeah.
Well, I guess the other question, if I may, so you mentioned the interpolating function. So what is that like? Is it the same for all galaxies when you try to fit galaxies?
Of course.
What is it? Yeah, what is it like? I mean,
it starts, as I said, starts linearly and goes to a constant.
Goes to a constant. So it's like a transition.
Right, but actually, I did not mention, but one of the great things about this sample is that these are galaxies that are all deep, very deep in the MOND regime. So all you need to know is the asymptotic behavior of mu, just it being linear. So there's not even an interpolation function. You simply, mu of x is x. In those galaxies, sorry. In those galaxies, you see transitions from Newtonian to non-Newtonian, and then you actually need the interpolating function, but of course, they all use the same.
Yeah.
Otherwise, it's...
No, I was asking because I remember there is an old paper by Luc Blanchet and Jérôme Novak, I think, where they were saying that in the solar system to explain flybys of Jupiter, you instead need a very sharp transition. Right. So can you, if I remember
it's a long story.
But, long, yes. Maybe we can talk about it later.
Yeah, it can be. It's okay. I mean, yeah.
Okay, thanks.
Other questions?
Yeah, thank you very much for a very nice talk. But I have a question about this relativistic theory, although you mentioned that is not the main topic. But so does it reproduce all MOND phenomenology? This one, this.
No, it was before.
That.
I think that one.
Before the data. Right here. Which one?
The new one. New.
Oh, I see.
Yes, score designers goes like
yes.
that. So.
No, but it's. Oh, I put it separately from others.
This one, yeah.
So does it reproduce all MOND phenomenology? Or?
Yes. That's what it goes in the non-relativistic regime. There was a slight thing that they claimed that there is a scalar that has a mass, but this mass has to be very small, and it just affects maybe in cosmology. But and anyway, it's a class of theories. It's not really a theory. You can see here. First of all, it has parameters. You cannot see them. But, there's several curves here with different parameters. And secondly, it's very complicated. So to be frank, it is showing the way to something perhaps, but I don't think it can be taken as the final MOND theory anyway. But it does, yeah, they all should go to non-relativistic.
So can I ask one more question about the A0? So do you think it's a new fundamental constant, or is it a kind of combination of?
No, I think it is a combination, that it is effective. I mean, I think this identification of A0 with cosmology is telling us that MOND, as we understand it now, is some effective theory. We have to understand it from more basic principles. The example I like to give is, suppose we do experiments just on Earth, and then we measure some G. Little G is it a fundamental constant? Galileo's little G, 9.81. And then we measure the radius of the Earth. We can measure some critical velocity, let's say the escape velocity from the Earth. And we notice with wonderment that this little g is v squared over r. So it's like the escape speed divided by the radius of the Earth, right? And we don't understand this relation if we just do experiments on that. But then, of course, with Newtonian gravity, we understand that it's just a derivable thing. It's only applies to the surface of the Earth.
Thank you.
Thanks. Elisa?
Thank you for the talk. What do you think about dark matter models that reproduce MOND behavior on small scales, like the the superfluid dark matter model? Superfluid dark matter.
Superfluid dark matter.
Yeah. I should say everything, of course, is put in by hand there, because this particular model has been shown not to work, but there are such models. So yeah, I don't like it. I tell you why. Because it is a hybrid, basically. It is you're trying to get the best of two worlds. You say, okay, MOND works on small scales, and and dark matter maybe works better in cosmology. So let's invent something. You see, this superfluid, it does not work as dark matter in galaxies. It doesn't work by adding to the gravity by just its presence, its gravitational presence as matter. It's not that. It works by changing the interaction between bodies. Okay, so it has to be understood that it's not a dark matter. I mean, on cosmology, it supposedly works as dark matter just by its gravitational presence, adding to the source of the Einstein equation. But in galaxies, it doesn't work that way. It works by changing the effective interaction between bodies. So it is a hybrid. It is and in principle, all over history, when with Copernican system and so on, there always attempt to sort of say, for example, in the solar system that, okay, all the planets actually do go around the sun, but the sun with all the planets go around the Earth because you want to preserve the centrality of the Earth, but also so I don't like them a priori, but also they have been shown to be in trouble. And yeah, and anyway, things are put in by hand in the theory to get MOND. So you invoke some superfluid that has very strange properties to get MOND behavior.
Thanks. Question?
Thank you for the talk. Do you think we could recover MOND by deforming the local Poincaré group that we use in gravity into a local de Sitter group? Because there would be like a natural acceleration scale.
I spent years trying to think about, but I didn't come up with any. Yes, but it's an obvious idea.
Yeah.
Yes. I have tons and tons of. It would be extremely nice if we could. It's a natural, right?
Okay. Thank you.
Naritaka?
Thank you for the nice talk. So I have a question about the last part you mentioned about the Henry effects and that's it. Well, no, I think the last slide, this one. I think this reminds me of the entropic gravities proposed by Farinde. Well, then the entropic force is caused by the change of the entropy of the digital horizon. So if we apply this idea to the digital space-time itself, then do you think it's relevant to the idea of entropic gravity?
You should have said that Verlinde's idea reminds you of this because
yeah, it sounds similar. So
because he used we pointed this out to, okay, so Verlinde had this idea of entropic gravity to reproduce Newtonian gravity basically, and then we pointed this out to him and he tried to modify. Again, in short, I don't think that he really has a point. Let's put it this way. If you follow his derivation, so to say, he knows what he wants to get, and and he could have gotten other things. So I don't.
I thought that once we use the first law of the thermodynamics, it may be relevant. But okay. But thank you very much.
Okay, so I think we are at time. If there are no other urgent questions, let's thank Madi again.
Thank you.